Greetings and welcome to the recitation video for Chemistry 221 problem set number 5. We're going to look at chapter 5 in this particular section. This section will look at both valence bond theory and molecular orbital theory. Pretty cool stuff. So like the previous problems, make sure you show all your work, use a periodic table. mhchem.org/pertab is the one that you should use because that's the one we'll use during quizzes and exams. You can definitely feel free to pause, rewind, move forward, scrub, speed me up to 1.5 speed, whatever you need to do in this video. You don't have to watch it from start to finish. Self-correct all of your work. The problems that are right, put some kind of self-correct symbol next to it so that I know that you know that's right. And if you miss a problem, no big deal. Just make sure you put down at least the correct answer, maybe cross out your old answer, put some notes down, stuff like that. I want to see a lot of work on your problem set. You turn in the problem set with all kinds of mistakes, full credit. You turn in the problem set with no self-correct marks, less than full credit. So it's really important. And if you have questions on any of this, definitely reach out to me or the Avid/LSC Tutoring Center located above the library at Mounted Community College. All great stuff. We're all here to help you. Very cool. While you're working on the problem set or while you're watching this video, there are a couple of handouts that'll be super important to you. The first is one we used in problem set number 4. It's the Geometry and Polarity Guide. It'll have all the names of the EPG and MG and the bond angles and polarity, all kinds of stuff. I encourage you to check that out. For this problem set, you're also going to need 2 molecular orbital diagrams. There are 2 separate ones we're going to use a lot. One is for boron, carbon, and nitrogen. So the MO diagram for B2 through N2, as well as a molecular orbital diagram that works for oxygen, fluorine, and neon, the MO diagram for O2 through Ne2. And make sure you have copies of these next to you, as well as the periodic table. You'll need them as you go through it, and it'll make more sense if you have them to look at. Okay, let's see what problem set number 5 has to offer us. Draw the Lewis structure of nitrogen trifluoride, NF3. What are the electron pair and molecular geometries? What's the hybridization of the nitrogen atom? And what orbitals on nitrogen and fluorine overlap to form bonds between these elements? At first, this question can seem kind of daunting. So what I'd like you to do on a question like this is just break it down, start with small chunks, and work your way up to the crazier, if you will, ones. And the first thing literally is just to draw a Lewis structure. A Lewis structure in problem set 2 is going to be really important for most of these problems, well, except for the molecular orbital problems like you'll see. But on this problem, definitely you want to start with the Lewis structure. From the Lewis structure, you can get the electron pair geometry, the molecular geometry. From the Lewis structure's electron pair geometry, you can get the hybridization of the central atom, which is nitrogen. And finally, from that, we can figure out what kind of orbitals overlap between nitrogen and fluorine in this molecule. So again, start just by drawing out the Lewis structure. You've got to have the Lewis structure. And if you've done it, this is going to be tetrahedral nitrogen. So again, how we got the Lewis structure, we added up the valence electrons. Nitrogen is in group 5, so it has 5 valence. Fluorine in group 7, so it has 7 valence. So 5 nitrogen valence electrons plus 7 times 3 valence electrons for fluorine. I believe that comes out to be 26 electrons that we have to make in the Lewis structure. Divide that by 2, 13 pairs. Start by having nitrogen in the middle, least electronegative, definitely compared to fluorine. Put the fluorines on the outside, connect them with a bonding pair. That's kind of the glue that holds the outside atom to the inside atom. And then you put lone pair electrons around the outside atoms first, and if you have any left over, you put it on the inside. So if you've done that, then this is the structure you get. Nitrogen has 3 bonds to fluorine. It also has a lone pair on it. No problem. Now, earlier I said how nitrogen is in a tetrahedral electron pair geometry. That's because the nitrogen has a lone pair and 3 bonding pairs. Anytime you have 4 pairs total, that's tetrahedral. If one of the pairs is a lone pair, then the molecular geometry is referred to as trigonal pyramid. All right. So this kind of stuff, I'm hoping, is a review from problem set 1. But again, if it isn't, don't be afraid to slow this down down, pause the video, make sure that you can get these answers before we go on. Okay, so far we've got the Lewis structure, we have the EPG and MG. It says next thing is the hybridization. And this is the new part now about problem set number 2. Problem set number 2 is basically about how to compare the different models used for why bonds form. And if it talks about hybridization, then it's referring to valence bond theory, sometimes referred to as hybridization theory. And there's a term used for the central atom, which describes how the atom's electrons kind of come together. And the important thing for you is that anytime you have electron pair geometry of tetrahedral, the hybridization is always sp3 hybridized, all right? Notice the nomenclature, S first, P superscript 3. Okay, that's really important in this kind of stuff. The hybridization is only reference to the central atom. So the fluorines are not sp3 hybridized. It's only the central atom, okay? So nitrogen is sp3 hybridized. Now the outside fluorines are using just their regular atomic orbitals. And if you remember from earlier times, fluorine is 1s2, 2s2, 2p5. That's the electron configuration of one fluorine atom. And of the 2p5, all the p's had 3 orbitals in the subshell. So when we took those 5 electrons, 1 electron each, that's Hund's rule, keeping them all separate. And then we pair only when there's no more room. So 2 of the 3 orbitals are paired, but one of the orbitals has a single electron in it. And that is the orbital. That's the 2p orbital, which is connecting to the nitrogen, okay? So all of the fluorines have a single 2p orbital, which is being used to combine with the central nitrogen. The nitrogen, when it says it's sp3 hybridized, that means that it takes, in nitrogen's case, the 2s and the 2p orbitals and mixes them together. It becomes sp3 hybridized. And when they mix, their energies become all equivalent. And if they're all equivalent, this leads to the tetrahedral geometry. In lecture, I drew I had much nicer pictures, but they look something like this, and this is kind of coming out of the screen. Anyway, nitrogen has 4 of these sp3 orbitals around it when it becomes hybridized. And you can see that nitrogen has a lone pair. One of the sp3 orbitals is 2 electrons, and that's the lone pair. But the other ones all have a single electron in them. And if you remember, nitrogen has 5 valence electrons because it's group 5. Well, there's the 5 electrons. 2 of them are a lone pair in one of the sp3 orbitals. The other 3 orbitals each have a single electron in them. So what happens then is you have one of these nitrogen sp3 orbitals with a single electron, and fluorine comes up, and sp orbitals were kind of like figure 8s, if you remember. But the important part here, one of those 2p orbitals has a single electron, and these two come together to make the nitrogen fluorine bond. One of the 2p orbitals has a single electron on fluorine. One of the sp3 orbitals on nitrogen comes together to make the bond. This is a head-to-head overlap. This is where the sigma bond comes in. Because these electron orbitals are kind of smashing together, that would be the sigma bond right there. Again, my drawing here is really bad. I apologize. But anyway, when we talk about bonding in this molecule, we would say that nitrogen is sp3 hybridized, and that means 4 sp3 orbitals. And one of those sp3 orbitals is combining with one of the fluorine 2p orbitals. The 2p orbital that we're bonding with has only a single electron. It always takes 2 electrons to make a bond. Pretty cool. So Punchline of this problem. Draw the freaking Lewis structure. Big surprise. Electron pair geometry will tell you what the hybridization is of the central atom. And anytime you see something tetrahedral, it's going to be considered sp3. And finally, when it comes to these bonds, it's only the central atom which has one of these fancy terms, sp3, sp2, whatever. So we would say that the nitrogen has an sp3 orbital that's combining with a fluorine 2p orbital. That head-to-head overlap creates the three nitrogen fluorine sigma bonds, or single bonds. So it's not too bad. Hybridization is kind of cool. It's something you can do when you get used to it, anytime, any place. You don't need fancy computers, and there is value in that, absolutely. However, we're going to see that molecular orbital theory does give better descriptions of molecules, but it's just so freaking complicated sometimes. It would be difficult for us right now to do a nitrogen trifluoride molecular orbital structure. That would be for a later class. So just realize it's kind of cool. It's not perfect, but it's all right too. So number 2, specify the electron pair and molecular geometries for each of the following, and then describe the hybrid orbital set used by the central atom. So again, hybrid orbital set just means hybridization. So on all of these, the first step, draw the Lewis structure, and the electron pair geometry will not only help you figure out the molecular geometry, but it will also help describe the hybridization or hybrid orbital set used by the central atom. So again, here's the first one, carbon diselenide. When you draw out the Lewis structure, there's 2 double bonds, kind of like CO2 we looked at in the last part. Anyway, the carbon in carbon diselenide is sp hybridized. We know that because carbon has an electron pair geometry which is linear. There are no lone pairs around carbon, so the molecular geometry is also linear, and anything that's linear is going to be sp hybridized. So carbon is using an sp hybrid orbital set to make bonds with those selenium atoms. For the next one, sulfur dioxide, when you draw out the Lewis structure, you can do it in several ways. However, the very best way to draw sulfur dioxide is like this, where the sulfur has 2 double bonds and a lone pair. Now remember that sulfur is period 3 and lower. It can go beyond the octet. This sulfur right now has 4 bonds and a lone pair, which would be 5 pairs. Sulfur can do this because, again, it's period 3 and lower. Now, why you would want to do this, if you drew this structure, all of your formal charges go to 0. So let's review that real fast. Sulfur is group 6. It has in this structure 2 lone pair electrons and 4 bonds, formal charge of 0. And the oxygens also have formal charges of 0. Oxygens also group 6, 4 lone pair electrons and 2 bonds goes to 0. If you have a sulfur-oxygen single bond and you figure out the formal charges, the sulfur becomes positive 1 and the oxygen with the single bond goes to negative 1. So just realize more formal charges of 0, a better structure. The very best way to draw this is with all double bonds like that. And again, sulfur can do it because it's period 3 and lower. But anyway, no big deal. The sulfur there is in a trigonal planar electron pair geometry, and the molecular geometry when there's 1 lone pair is called bent. And trigonal planar leads us to the hybridization of the sulfur, sp2. All trigonal planar electron pair geometries are sp2 hybridized. The next one is a compound called formaldehyde. We'll talk about that in the next chapter. But anyway, when you draw this out, the way to get all the electrons distributed is with a carbon-oxygen double bond. Remember, carbon needs to have 4 bonds around it all the time. Oxygen can't hog 3 lone pairs if carbon has only 3 pairs. So the best way is with a double bond. That carbon is also in a trigonal planar electron pair geometry. Molecular geometry the same, since carbon has no lone pair electrons. That carbon is also sp2 hybridized. And then the last one, ammonium, which is related to ammonia, but of course a little bit different. Ammonia is a nitrogen in 4 hydrogens all around it with a positive 1 charge. That nitrogen is tetrahedral for both electron pair and molecular geometries, no lone pair around the nitrogen. And anytime you have a tetrahedral electron pair geometry, the hybridization is considered to be sp3. Question number 3, draw the Lewis structure and then specify the electron pair and molecular geometries for each of the following molecules or ions. Identify the hybridization of the central atom. Okay, so then there's 4 possibilities here, XeOF4, OSF4, BRF5, and the central atom in what's called the tribromide ion. So again, how this works, draw the Lewis structure. The central atom, the electron pair geometry will lead to the hybridization. Now, before we do the first one, XeOF4, boy, this is sure one of my favorite molecules. And sometimes I cough not because I actually have a cold or need to cough. Sometimes I'm trying to drop a hint of something you might see in the future. So, XeOF4 is sure a cool molecule. Anyway, draw out the Lewis structure. If you're going to do it in the very best way possible, the xenon is in the middle of the 4 fluorines. There's a lone pair on xenon. And to make all of your formal charges go to 0, you should draw it with a xenon-oxygen double bond. Now again, xenon is certainly 3rd period and lower, so it can go more than an octet, and it's definitely doing that. This electron pair geometry is octahedral. You have 4 bonds to fluorine, a 5th bond to oxygen, and a lone pair that's 6 pieces, octahedral. And because there's 1 lone pair on it, the molecular geometry is referred to as square pyramid. Now, the electron pair geometry of octahedral implies that the hybridization will be sp3d2. And if you call it d2sp3, I have no problems with that. That's actually my preferred way, but this trend seems to be calling it sp3d2. Either way is fine. So sp3d2 for anything octahedral. The next molecule, OSF4, is a little bit tricky. Oxygen, if you remember, is 2nd in electronegativity only to fluorine. So what that means is fluorine would never be the central atom because it's the most electronegative. But oxygen is rarely the central atom too because it's 2nd in electronegativity only to fluorine. So when it comes to the atoms in OSF4, the oxygen is not the central atom. All right, it's actually going to be sulfur. Sulfur is lower electronegativity than the oxygen or fluorine, and the central atom is always the lowest electronegative atom. So in the molecule, do not put the oxygen in the middle, put the sulfur there. I don't know for sure why chemists a lot of times will write this as OSF4. I think they're trying to give you a hint about the structure of the molecule. The oxygen is connected to the sulfur, etc., etc. But anyway, just realize that's something that can happen. So if you draw out OSF4, this is the structure you're going to get right here. Remembering that sulfur likes to have formal charges equal to 0 whenever possible, you will get a little better structure if you draw a double bond O. If you do that, the sulfur gets into a formal charge of 0. The oxygen also gets formal charge of 0 with a double bond, and all the fluorines are formal charges of 0. If you have a sulfur-oxygen single bond, the oxygen will be -1 for formal charge, and the sulfur becomes +1. So again, the more zeros you have, the better. This is the very best way to draw this structure. Anyway, and sulfur, by the way, is period 3 and lower, so it can make more than 4 bonds, etc., etc. Okay, this sulfur has 4 fluorines around it and an oxygen, so 5 pieces. That means this is going to be the trigonal bipyramid. And since everything is connected to an atom, no lone pairs, the molecular geometry will also be trigonal bipyramid. Anytime you have trigonal bipyramid geometry, electron pair geometry, the hybridization is referred to as sp3d or dsp3. Either way is fantastic. The next one, BRF5, you got to count up all the valence electrons. Bromine definitely in the middle relative to the fluorines. And when you do this, you'll see that bromine has an extra lone pair on it. And again, bromine can handle more than 4 bonds because it's period 3 and lower, so no problem. So this bromine has 5 bonds to fluorine and a lone pair. That's 6 pieces total. Electron pair geometry is going to be octahedral. Because there's 1 lone pair on it, this is also going to be a square pyramid molecular geometry, like my beloved XeOF4 we talked about earlier. However, octahedral always means sp3d2 when it comes to hybridization, or d2sp3, no problem. All right, the last one, the tribromide ion, Br3-1. The central bromine will have 2 bromines connected to it, and when you draw out the Lewis structure, you should see that tribromide there, the central bromine has 1, 2, 3 lone pairs and 2 single bonds. So 5 clouds around the bromine. This is a trigonal bipyramid electron pair geometry. And because those lone pairs have to get as far apart from each other as they can, you can get all those lone pairs at about 120-degree angles if you put them in the plane of the molecule. So if you do that, then the bromines are at the 180-degree positions on the trigonal bipyramid. This is actually a linear molecular geometry, and because the bromines are opposite and the lone pairs surround it in that trigonal planar, this is actually a non-polar molecule. But anyway, that's neither here nor there. This EPG of trigonal bipyramid indicates this is also sp3d hybridization. Again, anything that's sp3d is trigonal bipyramid, anything sp3d2 is octahedral. Good to go. It says give the electron configurations for Li2, Li2+, and Li2- in molecular orbital terms. Compare the Li-Li bond order in 3 species, which has the shortest bond length. Okay, this is the first of our molecular orbital diagram questions. And if this is something new to you, just hang back. It's pretty chill, but it is a little weird at first, okay? Molecular orbital theory is the other big theory when it comes to figuring out how atoms come together. And in a molecular orbital diagram, if you do the complete version, you'll see the individual atomic orbitals on the left and the right, and in the middle you'll show the molecular orbital diagrams. So I'd like to try and draw here one, and again, my drawings are absolutely terrible, and I apologize. But anyway, on the left-hand side here, if you remember, lithium is a 1s2 and a little higher in energy. Lithium has a 2s1. So on the y-axis right here, this is an energy axis. And we talked about in Chem 221 how the 1s is closest to the positive nucleus, 2s farther away. So if you're going to react something with lithium, it's usually going to be the 2s because the 1s is held tighter, blah, blah, blah. Okay, this is like lithium atom number 1. And on the right-hand side over here, I'm going to draw another lithium atom. And that second lithium atom is also 1s2, 2s1. So this is now a second lithium atom. And you can imagine that if you're going to make lithium bonds, you're going to have individual lithium atoms at a long ways away where they can't make a bond. And what I've drawn there is basically the 2 individual lithium atoms when they're too far away. They're supposed to be the same energy, so 1s's are the same, 2s's are the same, etc., etc. Now, in the middle part here, I'm going to draw the molecular orbital diagram for dilithium. And when you have 2 atomic orbitals together, they make 2 molecular orbitals. And notice how one of them is lower than the 1s orbitals I drew, and one of them is higher. The lower molecular orbital, which is a sigma 1s orbital, this is called a bonding molecular orbital. And bonding molecular orbitals make the molecular orbital more stable. Like these make the glue that holds the atoms together. However, the higher energy orbital, which gets a little star symbol like that. So this would be sigma star 1s. That's called an anti-bonding sigma 1s orbital. Bonding orbitals make the molecule stronger. Anti-bonding orbitals make the molecule weaker. They try to destabilize it. In theory, the two atomic orbitals' energy is the same as the energy in the bonding and the anti-bonding. Bonding goes down just as much as the anti-bonding orbital goes up. Cool. Now, the 1s orbitals are far enough in energy from the 2s that the 2s orbitals make their own orbitals. And you can probably imagine that there's going to be a lower one and a higher one. The lower one is the sigma 2s orbital, and the higher one, sigma star 2s. So the bonding is sigma 2s, and the anti-bonding is sigma star. Sometimes on diagrams, you'll see little dot lines to show where the molecular orbitals came from. Every time you mix two atomic orbitals, you will get two molecular orbitals. The orbitals are the same. One of them will be higher energy, the anti-bonding, and one will be lower energy, the anti-bonding. So if this is lithium atom number 1, and on the right is lithium atom number 2. The middle part here now is the dilithium molecule, the Li-Li, okay? And what we can do is take the atomic electrons now and fill them into the molecular orbitals and see like what happens. So you have a total of 2 plus 2, total of 4 1s electrons. The lower 2 electrons are going to go in the sigma 1s orbital, and the other 2 electrons are going to go in the sigma star 1s orbital. Now we'll do the 2s interactions. We have 1 plus 1, 2 electrons. We always put them in the lowest molecular orbital first, so that's the bonding molecular orbital. And if you have any left over, they go in the sigma star. We don't have any left over. So this is now, this middle part, this is the dilithium molecular orbital diagram. Sigma 1s, sigma star 1s, sigma 2s, and empty sigma star 2s. And that's pretty cool. And from this molecular orbital diagram, there's lots of stuff you can do. So as an example, the sigma 1s and the sigma star 1s. Sigma 1s are bonding, sigma star 1s is anti-bonding. So those two interactions there kind of cancel each other out, all right? There's no net bonding going on there. But for me as a chemist, the exciting part comes from the upper part. Sigma 2s is filled, sigma star 2s is empty. So there's definitely more bonding electrons than there are anti-bonding electrons. And that can be a really cool thing. Now, if you want to formalize what this is, you can actually figure out the number of bonds. And this is the way that molecular orbital scientists determine the bond order. Bond order in molecular orbital diagrams equals 1/2 bonding electrons minus anti-bonding electrons. So for this diagram, you would say, okay, 1/2, and you can see how there are bonding electrons here and bonding electrons here. So that would be 4. And then I'll try and make a square around it. This one right here would be an anti-bonding. So it has 1/2 for bonding minus 2 anti-bonding, bond order of 1. And if your bond order is greater than 0, it should exist. So dilithium, Li2, exists, all right? It's a real molecule. If we would have calculated 0 for the bond order, then we would have said, oh no, nothing's going to happen. But in this case, yeah, we definitely have something going on. There's one more thing I'd like to show you here. You can see that what we've just done, by the way, is we've talked about the dilithium molecule, and everything so far is that. Oh, I forgot to say that if every up electron has a down electron, we would call this a diamagnetic interaction, a diamagnetic molecule. So dilithium itself is not really interested in magnetic fields because it has just as many up as it has down electrons. Okay. But one more thing. You can see the other part of this problem. You've got Li2 plus 1 and Li2 minus 1. Well, you can actually make these molecules. So let's say we wanted to do Li2 plus 1, all right? So what we would do in Li2 plus 1 is we would end up taking away an electron. So let me see if I can do this here. I'm going to try and white out, basically. Yeah, that electron right there. And the really cool thing here is that without that extra electron, that becomes Li2 plus 1. So check this out. I just made the molecular orbital diagram for Li2 plus 1. I literally just took away an electron from neutral Li2 to get the molecular orbital for Li2 plus. And from here, you can now reanalyze everything to see what bond orders are, magnetism. So let's figure out the bond order for Li2 plus. The bond order for Li2 plus will equal 1/2 bonding electrons minus antibonding. Well, I had to take out one of the bonding sigma 2s electrons, so now I have 3 bonding electrons, 2 antibonding electrons, bond order 1/2 for Li2 plus. And that is actually a legit molecule. Li2 plus is not as strong as Li2. The bond order is smaller than the bond order for neutral Li, but it is a molecule that exists. It's not as strong. As bond order goes up, the bond energy goes up. That's certainly not the case here. Bond energy would be less with a bond order of 1/2. Also, we now have an odd electron. This is a paramagnetic atom. It doesn't really ask for it here, but let's talk about it anyway. What the heck? Odd electrons mean paramagnetic, and if everything is paired like it was earlier for Li2, then it's diamagnetic. Notice how easy it was to make the ions, and that's a real cool thing. If we were to do this for a Lewis structure, all right, we could do it, but we'd have to try and use like dotted lines and stuff, and so and we have to redraw the Lewis structure, and that's a real advantage of MO. It's quite easy to make the ionic versions of these things. You start with a neutral version and move on. The last part of this problem is about Li2 negative 1. Now to make Li2 negative 1, I'm going to go back to neutral Li2. So I just added that other sigma 2s electron back. That's the electron configuration we had for neutral Li2. Li2 minus 1 means there's an extra electron. And that extra electron is going to go in an anti-bonding sigma 2s orbital. So notice here we've added now an additional anti-bonding electron. I'll try to make a square around it. So if we wanted to find the bond order of Li2 negative 1, once again, 1/2 bonding minus anti-bonding. And in Li2 minus, we have 2 sigma 1s and 2 sigma 2s, 4 bonding electrons. And in this structure, though, for Li2 minus, we have 2 antibonding sigma 1s and 1 antibonding sigma 2s. So we have 3 antibonding electrons. So we'll go 1/2, 4 minus 3. This is 1/2 for the bond order. So again, easy to make the ions because all I had to do was add an additional electron relative to neutral Li2 to figure this out. And like Li2 plus, Li2 minus is also paramagnetic. It has the odd electron now in the sigma star 2s orbital. This is going to be attracted to magnetic fields. Now, bond order, we saw in the last problem set, is inversely proportional to bond length. So what that means is bond order goes up, the bond length goes down. So biggest bond order will have the shortest bond length. And I bet you can probably see now that of all of these, the Li2 neutral will be shortest. Li2 neutral has a bond order of 1, and that's the biggest bond order relative to the Li2 plus and Li2 minus, which were both 1/2. So for these three molecules, we would say that Li2 has the shortest bond length. We can also say that Li2 plus and Li2 minus would have longer bond lengths. We don't know exactly if one is a little bit longer than the other, but they're both longer than Li2. This is the kind of information you can get out from molecular orbital diagrams. So again, the molecular orbital diagrams can be pretty cool for different things. Now, this is my cheesy hand-drawn version. I don't think I actually said anything about magnetism, but I'm throwing it in because we'll talk about it later anyway. Let's go back to a more formal version. This is the dilithium molecule. And again, on the left, we have Li lithium atom number 1, if you will. And on the far right, we have lithium atom number 2. And then this part in the middle is the dilithium molecule itself, and it's an energy axis on the y-axis, so you can see they're getting larger and stuff like that. Not everybody likes to draw pictures like I just did on the last slide there of dilithium, lithium plus 1, lithium minus 1. So I think this is a good time also to talk about the shorthand notation. All three of these molecules here are listed in shorthand notation. So dilithium, the one at the bottom, it starts off in the sigma 1s orbital, and there's 2 electrons. So notice that symbolism. It's like a parentheses with the name of the orbital inside, and then a superscript represents the number of electrons. So dilithium has sigma 1s2, sigma star 1s2, sigma 2s2, and an empty sigma star 2s. You actually don't need to include that at all if you don't want to. Either way is fine. And the bond order, 1/2 the bonding 4 minus anti-bonding 2. And remember that star means anti-bonding. 1/2 parentheses 4 minus 2, bond order of 1. So this is the shorthand notation, and there are some pretty serious advantages of it. You don't have to draw out the diagrams, blah, blah, blah. And like we saw in the last part that I hand drew, Li2 plus would have 1 less bonding electron, so 1/2 parentheses 3 minus 2, 1/2. Li2 minus in the middle right there has all bonding electrons, but it has an extra anti-bonding electron. So bond order also is 1/2 there. And again, because bond order is highest for Li2, that would mean Li2 is the shortest, all right? Bond order is highest, Li2 would have the shortest bond length. We would say that Li2 plus and Li2 minus are both longer than Li2, but it would be hard to know exactly which one was longer or shorter since they have the same bond order. So this hopefully gives you a good sense of how molecular orbital diagrams work. Once you see them, they're pretty chill, but at first it can be a little bit weird. This would be a good time to go back and watch the first part of this problem if you're still having questions, but it's definitely something you can get, okay? Cool. This question says oxygen can acquire 1 or 2 electrons to give O2 minus 1, sometimes called the superoxide ion, or O2 minus 2, the peroxide ion. Then it says write molecular orbital configurations for O2, O2 minus, and O2 minus 2. Remember to use the molecular orbital diagram for O2, F2, and Ne2 when constructing the diagrams, and for each of them determine the magnetic character, and that means paramagnetic, diamagnetic. It also wants to find the net number of sigma and pi bonds, bond order, and the relative bond length. Okay, so just like in the last example, all right, for dilithium, we're going to start by drawing the neutral oxygen molecule, O2, okay? And I'm going to kind of, because this is more of a horizontal screen than a vertical screen, I'm going to draw the 1s and 2s on the left, and I'll draw the 2p on the right. Officially, 2p should be above the 1s and 2s, but because of the constraints of the screen, I'm going to do it this way. So when you're drawing molecular orbital diagrams, again, you want to have the atomic orbitals on the left and the right, and then the molecular orbitals in the middle. So this first part, we're going to start off, and we're going to have the 1s and 2s atomic orbitals, and because there's 2 oxygen atoms, you're going to have 2 of them. And then over here on the left, I'm going to put the 2p orbitals. And if you remember from Chem 221, oxygen has 8 electrons total. So that's 1s2, 2s2, and 2p4. And remember, by Hund's rule, you put 1 electron in each orbital, spread them out, and only pair them up when there's nothing left. So I just drew the electrons for the first oxygen atom. I would do the same thing for oxygen number 2. It would also be 1s2, 2s2, 2p4, and I'll have them separate. All right, no problem. Like before, 2 atomic orbitals make 2 molecular orbitals. One of them will be lower, the bonding orbital. One of them would be higher, the anti-bonding version. So for this one, the lowest one is going to be starting off just the same as dilithium. This is a sigma 1s, and a little bit higher, sigma star 1s, the anti-bonding. Then you'd have a sigma 2s, and higher energy, sigma star 2s. And if you want, you can make little dots like that to show like where they come from, okay? Let's do this part first. So using blue for the electrons. The 1s electrons, there's 4 of them. The first 2 go in the sigma 1s, and the next 2 go in the sigma star 1s. Then the 2s electrons, the first ones go in sigma 2s, and then the last 2 go in the sigma star 2s. Now notice that this part, we have just as many bonding as anti-bonding electrons. And if you think about it, if you have just as many bonding as anti-bonding, there's not going to be any interaction in those molecular orbitals. So one thing that's kind of cool, those electrons, all of them listed there, you can kind of think of them as a type of a core electron. They're not involved in the molecular orbital diagram. However, the other part here with the 2p's is definitely worth talking about. Now notice the note up there. It said oxygen, fluorine, and neon. There are 2 forms on how the 2p orbitals come together. Because we have 3 2p orbitals mixing with another 3 2p orbitals, this middle part is going to have a total of 6 molecular orbitals. But it makes a difference if you have O2, F2, and Ne2 versus the other 3. I called them NBC. It's the B2, C2, N2. So if you look at the diagram for the OFNE, I called them phone, F-O-N-E, like a telephone, or anyway, whatever. Anyway, if you do that, for the OFNE, you end up with a 1, 2, 2, 1 configuration. So notice that there are 3 bonding molecular orbitals, which are lower in energy, and there are 3 anti-bonding molecular orbitals. So that part is cool. The lone single ones are sigma. So this is a sigma 2p. The next 2, which are at the same energy, are pi 2p, and all of those are lower than the atomic 2p's they're coming from. But then the higher 2 orbitals up there are the anti-bonding pi star 2p, and then the highest one there, sigma star 2p. And again, you can draw little dots here, and again, I recommend looking at an actual diagram because my drawings are horrible. I apologize, I can't draw, but hopefully you can see that there's kind of a 1, 2, 2, 1 configuration. Sigma 2p followed by the 2 pi 2p, then the 2 pi star 2p, then the final sigma star 2p. Okay, now just like before, we're going to put the electrons in these orbitals. We're going to start at the bonding orbitals and work our way up to the anti-bonding. And there's a 2p4 on the left and another 2p4 on the right. That's 8 electrons total. So the first 2 electrons are going to go in the sigma 2p. That'll fill that up. The third and the fourth electrons will each go in the pi star 2p. Hund's rule says that each one has to have its own house first, and then you start pairing up after. So initially, you put them in individual molecular orbitals. The fifth and the sixth electrons go there, so they do pair up pi 2p. And then the interesting ones, arguably, 7 and 8, those are each going to be 1 each in the pi star 2p. Well, this is the molecular orbital diagram now for O2. And notice some interesting things about this. First of all, the molecular orbital diagram has two unpaired electrons. So O2 is paramagnetic, all right? O2 has odd electrons. And why that's kind of cool is because if you look at the Lewis structure for O2, like if you drew out O2, it would be an oxygen-oxygen double bond with two lone pairs off each oxygen. Well, nothing in the Lewis structure looks paramagnetic. All right, we have bonding pairs between the atoms. We have lone pairs on the oxygen, but there's no single electrons. So MO diagram is actually a better way to describe O2. In the lecture notes, I showed a video. Liquid oxygen is attracted to magnetic fields. If you looked at just the Lewis structure there, you wouldn't expect that. So, MOs are really cool. It's a better version. Anyway, so hopefully this gives you a sense for the power of molecular orbital diagrams. When it comes to magnetism, you can see that O2 is paramagnetic because it has odd electrons. That's pretty neat. Bond order, remember, is 1/2 bonding electrons minus anti-bonding electrons. Now, I'm sometimes known, or I call myself, the lazy chemist, because I don't like to do things if it's just a waste of my time. And if you look at the sigma 1s, sigma star 1s, sigma 2s, sigma star 1s, we have sigma star 2s, we have just as many bonding as anti-bonding electrons there. So when it comes to bond order, you can ignore filled sets of orbitals. You can ignore sigma 1s interactions and sigma 2s interactions because they're all going to cancel out. You really only have to focus on bond order for the outer ones, and that's going to be the 2p interactions. So what I'm going to do here is I'm just going to focus on the bond order for the sigma 2p area. And if you do that, all right, you can see that there's two, let me circle them here. Let me use blue, I guess. There's 2, 4, 6 bonding electrons. And if I put them in squares, trying to do what I did in the last problem, there would be 2 anti-bonding electrons. So the bond order for O2, 1/2 6 minus 2, 1/2 of 4, 2. All right, so the bond order for MO is 2. And that corresponds pretty well with the Lewis structure down there, because the Lewis structure has a double bond, all right, and that would be a bond order 2, stuff like that. Now, one thing we haven't talked about yet is sigma and pi bonds. In the dilithium example, all of those were sigma bonds because the electrons, the net bonding electrons, were resided in sigma bonds, all right? For molecular orbital diagrams, notice that you have sigma interactions. Let me use a different color here. You've got sigma interactions, and up here, although it's empty, is anti-bonding sigma. So if you want, the number of sigma is just 1/2 the bonding sigma, 2, no anti-bonding sigma up above. This means there's 1 sigma bond in this molecule. So this is actually another cool application of MO. It allows you to find number of sigma bonds. Now, the number of pi bonds, actually, let me use a different color here. The number of pi bonds, I'm going to use this yellow color, is the bonding pi's minus the anti-bonding pi's. So in that kind of orangish triangle there, there are 4 bonding pi electrons and 2 anti-bonding pi. That means 1 pi bond. And that corresponds again really well with the Lewis structure, because the first line you draw is a sigma bond, the second line you draw is a pi bond, and sigma plus pi equals bond order. So this works out really well. And in the molecular orbital diagram, it's the same thing. Sigma plus pi equals bond order. 1 sigma plus 1 pi. We're good to go. So what we did there was we just drew, in my sloppy handwriting, the molecular orbital diagram for O2, neutral O2. It's got a sigma bond, it's got a pi bond, it has a bond order of 2, it's paramagnetic. Pretty cool. Now, let's talk about O2 -1 and O2 -2. If you're going to draw those, O2 -1, it would have one more electron. So I tried to draw there, it's being sloppy, one more electron, a paired electron in a pi star 2p. So if you do for O2 -1, bond order, 1/2 bonding minus antibonding. I haven't changed my number of bonding electrons, but now I have 3 antibonding electrons. I just put one more antibonding electron in there. So bond order of O2 -1, 1.5. Notice how the bond order went down relative to O2. That'll be helpful here in a little bit. Now, O2 -1 is still paramagnetic because it still has that odd electron right there. That electron doesn't have a partner to it. However, the number of sigmas is now, and pi's will be different somehow. Remember that number of sigma plus number of pi has to equal bond order. And since bond order has gone down, either sigma or pi have changed. Now you can probably see that the sigma antibonding electrons have not changed. We still have 1/2, 2 minus 0. We still have one sigma bond. But number of pi's, well, we still have 4 bonding pi's down there in that lower square, but we now have 3 anti-bonding pi's, 0.5 pi bonds. So again, you can have fractional bonds pretty easy in molecular orbital theory. This is 1/2 of a pi bond in the superoxide ion there. So just very quickly there, we found all the information for O2 -1. Again, we started with neutral O2 and worked our way up. We're going to do the same thing now for the peroxide ion, the O2 -2. And what I'm going to do, I'm just going to add one more electron there. I'm going to pair up the other antibonding pi electron. So O2 -2, every up has a down electron. O2 -2, diamagnetic. Every up has a down. O2 -2 is not as interested in magnetic fields as O2 and O2- were, and that's kind of a neat thing, I guess, if you're into this stuff. Anyway, I digress. Bond order for this bad boy, 1/2 bonding minus antibonding. Still haven't affected the bonding electrons, but I added one more electron, which went in an antibonding pi orbital. 1/2, 6 minus 4. 1 is the bond order. So notice that bond order here is going from 2 in neutral oxygen to 1.5 in the -1, and now to just 1 in O2 -2. Haven't affected the sigma bonds at all. I still have 2 bonding, and the very top anti-bonding sigma star is unoccupied, so that means 1 sigma bond. And at this point, you could just stop and say, well, there's not going to be any pi bonds because bond order equals sigma plus pi. I have 1 sigma. The bond order is 1, so pi must be 0. But I know, don't believe anything. It's okay. No, seriously, I want you to question everything. Never take anything I say for granted. Question everything. Anyway, number of pi, 1/2 bonding pi, 4. Now we have 4 anti-bonding because all the pi stars are filled up at this point. You can see that sure enough, 0 pi bonds. So O2 -2 is diamagnetic, bond order of 1. It's 1 sigma bond, 0 pi bonds. We're good to go. The final thing is D. It says relative oxygen-oxygen bond length. So remember, as bond order goes up, the bond length goes down. So we would say that O2 neutral with a bond order of 2, that would be the smallest bond. And again, I'm saying that because biggest bond order, smallest bond length, all right? On the other hand, O2 -2 there, with a bond order of 1, that would have the longest oxygen-oxygen length. It has the longest bond length. Bond order goes down, bond length goes up. So smallest bond order means biggest bond length, and O2 -1 would be somewhere in the middle. So this is super sloppy. You can see how MO can get kind of weird sometimes. I'm now going to show you the computer-generated versions, if you will. I'm going to show you the neutral O2 molecular orbital, and then I'll have shorthand notation for the other parts. So here's the computer version of the O2 diagram. Again, you can see the 1, 2, 2, 1 there a little bit easier. Sigma followed by pi to 2 pi stars, and then the sigma star. And again, neutral O2 has 2 unpaired electrons, which is pretty neat. So when it comes to O2, this would be the shorthand notation. Notice the core electrons part. Sigma 1s and sigma star 1s were filled. They both had 2. And just like in electron configurations in Chem 221, we would use the noble gas notation sometimes to do electrons. So you could write magnesium's electron configuration as neon 3s2, all right? This is the equivalent version now in molecular orbital theory. You can write core electrons in square brackets. Then you have sigma 2s with 2, sigma star 2s2, etc., etc. The shorthand notation is all right, but notice here pi star 2p. It may not be as obvious that this is paramagnetic unless you actually draw out the structures over here, which is what we're seeing on the right. Now, O2 minus 1 just has one more electron in that pi star 2p. And again, you'll pair up one of them, either one or the other, doesn't matter. That's what the pi star 2p is. And then O2 minus 2, as I tried to show in the last slide too, both of them are filled. So the pi star 2p is totally filled. And you can see how you have just as many pi star electrons as pi electrons, no pi bonds there. When it comes to these different properties, we saw that O2 was paramagnetic. O2 minus 1 still had a single electron, so it was paramagnetic. But O2 minus 2, where there were just as many up as down electrons, diamagnetic. We talked about how the sigma interactions came mostly from the sigma and sigma star interactions. And sigma star was empty in all of these. So the sigma bonds won't change, but the pi bonds certainly do. So sigma bonds go 1 to 1 to 1 because we never added any sigma star electrons in these problems. But the pi bonds went from 1 to 1/2 to 0 as you added in those anti-bonding pi electrons. Pi bonds certainly changed. Bond order we saw went from a 2 for neutral O2 to 1.5 to 1. And again, what I'd like you to see is that sigma plus pi equals bond order. So sigma plus pi equals bond order, sigma plus pi equals bond order. That can be kind of helpful sometimes. And as bond order goes up, bond length goes down. Oxygen, neutral oxygen has the biggest bond order, so it's the shortest length. On the other hand, O2 minus 2 had the smallest bond order. It'll be the longest bond length. If you can do this problem, you've got this stuff down. I do want to show you here in a little bit an example of the quote-unquote NBC diagrams. The only difference between those and these is that the 1, 2, these sigma and pi's will trade places, but everything else is the same, and you can do the NBCs just as easily as you can the OFNEs like this one. Here's an example of the nitrosyl ion, NO+, and it has an interesting chemistry. And then this is going to be a molecular orbital question. So one thing I want to point out is this question is a little different because we have oxygen, which is from the OFNE side of the molecular diagrams. We also have nitrogen, and that's from the NBC diagrams. So the question might be at first like, wow, which one do I use? And most of the time, when you have alternate species like that mixing, almost all the time you want to use the OFNE molecular diagrams. So in this problem, we're going to use that 1, 2, 2, 1 diagram that we just used for the oxygen problem earlier. And if you do have a question about that, then by default, you want to use the phone 1, 2, 2, 1 diagram, not the NBC. Anyway, then this question, is NO plus diamagnetic or paramagnetic? How many electrons? It talks about the LUMO and the HOMO. What's the NO bond order? And is NO stronger or weaker in NO than NO plus? Well, of course, you have to start by drawing the molecular orbital diagram. And we're using the OFNE, the 1,2,2,1. And like the dioxygens, the 1s and 2s interactions are going to be totally filled and honestly not that exciting. So this is the molecular orbital diagram for NO plus. And you can see here, here's the 2s interaction, or the 2s interactions, and this is the 1,2,2,1 interaction between the NOs. Now remember, it's NO plus, so I took away an electron. Normally oxygen is 2p4, but you can see it's just 2p3. I took the electron away from that side. If you took it away from the nitrogen side, that's fine. But the important part is you're going to have a total of 6 electrons. They're going to go in the lower sigma 2p, followed by pi 2p, pi star 2p, and sigma star 2p. They used S for sigma and P for pi. That's kind of a cheesy thing to do, but you do see it sometimes. So just FYI on that. Anyway, once you have the molecular orbital diagram, first of all, you can see that this molecule in the middle, the molecular orbital part, every up electron has a down electron. So NO plus is diamagnetic. And here's a little hint too. NO plus, if you figure out the valence electrons, nitrogen is 5, oxygen is 6, but you take away 1 for the positive, 10 electrons. Most of the time, that means it's going to be diamagnetic. Now, you have to be careful of that, because in this diagram, if you would have had 8 electrons, you could have had individual electrons in the pi orbitals. But generally speaking, even number of electrons often will be diamagnetic. The second one, I wanted to introduce the terms HOMO and LUMO, and those are used a lot in molecular orbital theory. HOMO stands for highest occupied molecular orbital, i.e. the last molecular orbital where you have electrons. And in this diagram, the HOMO is the pi 2p. That's the last set of molecular orbitals with electrons in it. The LUMO is the lowest unoccupied molecular orbital, i.e. where will electrons go if you add extra ones to it. So the lowest unoccupied molecular orbitals would be the pi star 2p. So again, this one is the HOMO and this is the LUMO. The HOMO-LUMO gap is actually pretty important for these things. A lot of times that will be used to figure out the kind of light needed to make the transition possible. It'll also help you figure out the energies and stuff like that. So because here's the shorthand notation of the NO plus electron configuration, the HOMO is literally the last orbital that's filled up, and that's going to be the pi 2p. The LUMO would be the next one. So if you added one more electron, i.e. on answer D, when we make neutral NO, where does the electron go? That would go in the pi star 2p. Bond order, 1/2 bonding minus anti-bonding. If you include all the bonding electrons in the diagram on the right, you would take 1/2 parentheses 2, 4, 6. And again, this is bonding down here. These are bonding right here. So 2, 4, 6, 8 bonding electrons. And then I'll try and make a triangle, I guess. The anti-bondings would be these guys right here. There is a total of 2 anti-bonding electrons and those kind of diamond-looking things. So the bond order here is 3. No problem. But the interesting part is do you think that NO would be stronger or weaker than NO plus, or actually the vice versa? Well, neutral NO, we would have to add an electron to the LUMO, pi star 2p, and that's an anti-bonding molecular orbital. So neutral NO has one more anti-bonding electron than NO plus does, and that makes the bond order of NO go to 2.5. If you figure it out, 1/2 parentheses 8 minus 3, that would be the NO neutral bond order, and bond order has gone down in neutral NO relative to NO plus. So we would say that NO plus has a stronger bond. It has a bigger bond order. It's going to be harder to break up than neutral NO. So in this case, the ion is actually stronger than the neutral atom it came from. And that's the kind of cool stuff you can do with this kind of molecular orbital information. This problem has nitrogen, N2, and it can make N2 plus or N2 minus 1. Use molecular orbital theory to compare these three species with regard to magnetism, which is paramagnetic, diamagnetic, number of pi bonds, bond order, bond length, bond strength, no problem. Okay, this is an example now where we're going to draw a molecular orbital diagram with the quote-unquote NBC. And NBC, the nitrogen, boron, and carbon version, looks a lot like the OFNE we did on O2 earlier and NO plus just a little bit ago, but there's a little bit of difference in how the bonding electrons go in. So like before, I'm going to try and draw the neutral N2, and I'm going to start by putting the 1s and the 2s kind of here on the left, and I'm going to have a second nitrogen, so 1s, 2s, and then like before, I'm going to try to have the two P's. So again, the left-hand side, 1s, the right-hand side is the second nitrogen. And like before, they're going to come together to make bonding and anti-bonding. And same thing up here for 2s, sigma 2s and sigma star 2s. And you can do this kind of thing. If you're kind of an artist, you'll probably dig this kind of stuff, and I can do it. I don't know, it always feels cheesy to me. Anyway, the important part, stop babbling, Michael. Important part here is the 2p interactions. The 2p interactions are different for NBC versus OFNE. And in the OFNE, it was a 1-2-2-1 configuration where sigma was first, followed by pi, then pi star, then sigma star. Well, when you have NBC, so for things like N2 here, or C2 or B2 or Cn minus, stuff like that, what happens is it goes 2-1, 2-1. The pi 2p's are lower than the sigma 2p's, but the pi stars are the same and the sigma star is the same. So notice here, it's kind of like a 2-1, 2-1. That's what I was referring to. Pi 2p is lowest now, followed by sigma 2p, then pi star 2p, sigma star 2p. And again, you can draw little dots. Anyway, nitrogen is 1s2, 2s2, 2p3, total of 7 electrons. The second nitrogen in N2 will also be 1s2, 2s2, 2p3, okay? And like before, let's mix the atomic electrons in the molecular orbitals. Total of 4 electrons in the 1s, so sigma 1s, sigma star 1s, they cancel. Sigma 2s, sigma star 2s, they also cancel. So you can see there's really nothing going on in the 1s or the 2s. But like with O2, the interesting part comes in the 2p's. We have a total of 6 electrons, so the pi 2p's get 2 first, 3, 4 pairs them up, 5, 6. Voila, this is the N2 molecular diagram. And again, you can see same process as we've used before. It's just that in these guys, the pi 2p's are lower than the sigma 2p's, and that can be kind of important. Like before, you can make N2 plus and N2 minus pretty easy. So let me kind of have up here kind of an overall view. We're going to put N2, I'll put N2 plus, and N2 minus, okay? So magnetism, N2 is dia because every up electron has a down. Number of pi bonds, well, let me use a different color, I guess, for pi. Pi is going to take the pi bonding and the pi star anti-bonding. And pi bonds, 1/2 parentheses bonding minus anti-bonding, 1/2 parentheses 4 minus 0. N2 is going to have 2 pi bonds. Bond order overall is going to be 1/2 bonding electrons minus anti-bonding. You can ignore all the 1s and 2s interactions because they equal each other out. 1/2 6 minus 0 is going to be a bond order of 3. I'm going to keep bond length and bond strength here a little bit to the end. Let's do the other parts first. Bond length and bond strength are relative things based on their bond order, so that's kind of important. And although the question didn't ask for it, this molecule would have one sigma bond because there's two bonding sigmas and no anti-bonding sigmas, stuff like that. Okay, now N2 plus 1, which is the next one, I need to take away an electron. So I'm going to take away one of the sigma 2p electrons. So I've tried hard there to make, kind of sloppy there, I've tried hard there to make it show there's only one sigma bond, okay? Now this is an example where we've taken away a bonding electron, and it will affect everything just as much as we've seen. First of all, with only a single electron, N2 plus is paramagnetic because it has a single sigma 2p electron. That's going to make it paramagnetic. Pi bonds, notice I haven't touched my pi electrons in N2 plus, so believe it or not, the number of pi bonds will still be 2. All right, we still have 4 bonding pi's, no anti-bonding, so still 2. However, I have lowered the number of sigma bonding electrons. So when it comes to bond order, 1/2 parentheses 5 minus 0, this is going to be 2.5 for a bond order. So you can see how this works, pretty chill, as we've always done. Now, N2 minus, I need to put my neutral N2 back, so I'm going to add that electron back in. N2 minus has one more additional electron, and the LUMO, the lowest unoccupied molecular orbital, pi star. So I'm adding here an anti-bonding pi electron, which will do some weird things here in a little bit. So, back to the list. Magnetism, well, N2 minus also has an unpaired electron. It's in the pi star area, so this thing is paramagnetic. Now, number of pi bonds. Now I still have 4 bonding pi's, but now I have an anti-bonding pi. So 1/2 parentheses 4 minus 1. You can see that the bond order now is 1.5. We have 1.5 pi bonds now instead of 2. Anti-bonding electrons tend to lower the number of bonding things. The bond order for N2 minus, 1/2. Again, I'm just looking at this 2p's because who cares about the 1s. Bond order 1/2 parentheses 6 minus 1. Bond order is also 2.5. Okay, so there's the results of the different magnetisms, pi bonds, sigma bonds. That actually doesn't have sigma bonds, sorry about that. All of the molecules will have one sigma except for N2 plus, which would have half of a sigma. And I know that because remember, bond order equals number of sigma plus number of pi's. So we have the bond order, we have the number of pi bonds, take the red number, subtract the green number to find the number of sigma bonds. Anyway, the last two things there are in bond length and bond strength. This is a relative kind of an expression. As bond order goes up, the bond length goes down. So we would say that N2 is probably the shortest, and these two I would just refer to as longer, all right? They're about the same, but we don't have enough information to tell. So we would definitely say that N2 is the shortest. N2 plus and N2 minus will be longer than that. They're probably close to the same, but we don't honestly know more than that at this point. As bond order goes up, the bond strength also goes up. So the bond strength would be largest for the N2. It would take the most energy to break it up because of that higher bond order. And these two would be smaller bond strengths. They're smaller. I don't know which one is small s and stuff. So notice that when it comes to bond length, bond strength, and stuff like that, it's a relative thing, all right? And if you have two values which are the same, like N2 plus and N2 minus, honestly, it's hard to know, all right? So we can say that they're both of the ions are longer than the shorter N2, and they have a smaller bond strength relative to N2. So this is your instructor's very cheesy way of drawing this out, and I hope it's helped. I want to show you now a computer-generated version, which hopefully has some use to it too. This is neutral N2. You can see how the pi's are lower than the sigma. Then we go pi star, sigma star, stuff like that. N2, this is the shorthand notation for that. Core is again showing 1s, which are boring. Honestly, 2s's are kind of boring too, but pi star, pi 2, p4, sigma 2, p2, that's the bonding electrons in N2. And then N2 plus, we would just take away what the highest occupied molecular orbital electron, so it only has a single electron in sigma 2p. N2 minus, we would go back to neutral N2 and add one more to the HOMO highest, or excuse me, the LUMO lowest unoccupied molecular orbital. That would be pi star 2p. Then here's the results of the other parts we talked about. N2 is diamagnetic, while the other twos are para. They have 2 pi bonds, except for N2 minus 1, because we put an extra electron in the anti-bonding pi. Bond order 3 versus 2.5 for the other ones. So when it comes to bond length, N2 should be the smallest. N2 plus and N2 minus, about the same. They're longer. That's all we can really say. And then N2 plus and N2 minus would be weaker than N2. N2 would have the biggest bond strength. The other two would be weaker, probably about the same. That's as much information as we have, very relative scale. So hopefully by going through these examples, you've got a good understanding for what MO is, and you can knock these out. We're only looking at simple examples, excuse me. We're only looking at molecules up to dineon, only diatomics, but in this you can hopefully get a sense of the power of the things you can glean from a molecular orbital diagram analysis. This compound is called phosphorine. It's a less common amino acid, and there's the structure for it right there. And what I'd like you to do is describe the hybridization of atoms 1 through 5 and the angles of bonds A, B, C, and D. So for this problem, we're jumping back to hybridization, Lewis structures, stuff like that. And the punchline of both answering both A and B is we're going to need to figure out the electron pair geometry of those different P's. So let's look at atom number 1 up there, which is at the top. And atom number 1 is a carbon with a double bond and 2 single bonds, okay? And that means that carbon is trigonal planar, all right? And that's going to be helpful because that means that atom number 1, that carbon, trigonal planar, is sp2. Anytime you have trigonal planar, things are sp2 hybridized. Also, the angles, anything that's trigonal planar will be 120 degrees. So you can see there how electron pair geometry helped with both the hybridization and the bond angle. We were able to knock all these out, no problem. So again, the punchline, electron pair geometry will help you find both the bond angles and the hybridization and a whole bunch of other stuff too, but this is the important part. So carbon number 1, trigonal planar, is sp2. All the other atoms listed there are tetrahedral. So if you look at atom number 2, it's an oxygen, 2 lone pairs and 2 bonds, tetrahedral, sp3, all right? The nitrogen there, atom number 3, is also tetrahedral. Carbon 4 is tetrahedral. Even phosphorus there is tetrahedral. So they're all sp3. And you probably can guess that if they're all tetrahedral, that means all the other bond angles will be, if you said 109 or something like that, you're good. Yeah, all the other bond angles are going to be 109. Angle A, of course, is trigonal planar, so that would be 120, but all the rest of them, 109. And again, you put 109.5, 107, that's fine. 109 is a really good average of all of those. Sketch the Lewis structures for ClF2 plus and ClF2 minus. Notice that's a chlorine with 2 fluorines. It is not a chlorine, or excuse me, it is not a carbon iodine fluorine. That's very important. If you ever have questions about that, you have the right to ask me. I don't want you to be confused about being carbon iodine fluorine or what it should be in this case, which is chlorine with fluorine. Anyway, what are the electron pairs compare molecular geometries. Do they both have the same angles? What hybrid set is used? So, big surprise, draw the Lewis structure for ClF2 and ClF2-1. Here's ClF2. Now, from this molecule, you can see the central chlorine is in a tetrahedral electron pair geometry, 2 lone pairs and 2 bonds, tetrahedral. We would refer to this as a bent molecular geometry. Anytime you have tetrahedral, that means sp3 hybridized, and the angle will be about 109 degrees. ClF2-1, though, is a little bit different. The central chlorine has 3 lone pairs around it with still 2 bonds to fluorine. This is a trigonal bipyramid electron pair geometry. The molecular geometry here will be linear. You need to keep the lone pairs as far apart from each other as they can. This is sp3D hybridized. Trigonal bipyramid always means sp3D. And finally, because it's linear, the FClF angle, 180 degrees. While ClF2 plus is polar, ClF2-1 is nonpolar. And that's kind of an interesting thing you can glean from this kind of analysis. Here's a problem where we're comparing CO2 with CO3-2, the carbonate ion, and we're going to think about them in terms of bond angles, bond order, hybridization, and finally we're going to compare both of those to carbon monoxide, CO. So, big surprise, first thing you need to do, draw the Lewis structures. Carbon dioxide is a carbon-oxygen double bond on both sides. It's linear. Carbonate is a molecule that will resonate. So when you first draw carbonate, you have to have a double and 2 single bonds, but it doesn't matter where the double bond is located. It can be located on any of the 3 structures there. So carbonate will resonate like that, and that's kind of important. And later when we talk about carbon monoxide, you draw the Lewis structure out. Carbon and oxygen have to have 4 bonds. Oxygen doesn't like making a triple bond, but it has to because carbon must have an octet. It must have 4 pairs, so it's got a triple bond. So, bond angles here. The carbon in carbon dioxide, that's a linear electron pair geometry, that would be 180. Carbonate, the CO3 resonating thing, that's trigonal planar. That's going to be about 120 degrees. And carbon monoxide is just straight across, only 2 atoms. You can't really have a bond angle with 2 atoms, so I'll just put 180 in parentheses, in a quotes there. It's not really a bond angle, but if you have to think about it, that's what it is. Now, the next part is more interesting. Carbon dioxide has 2 carbon-oxygen double bonds. Double bonds are bond order 2. Carbon monoxide on the bottom, that's a triple bond. That would be bond order 3. But carbonate, because it's resonating, you take the total number of bonds, the total number of lines between carbon and oxygen, and there are 4 lines, and you divide it by the number of places those bonds or lines can go. There are 3 places. So the bond order for carbonate, 4/3, which is kind of wild. And then finally, the hybridization is based on the geometry. CO2 would be sp. CO3-2 is trigonal planar. That would be sp2. Carbon monoxide, you can argue, is sp3 hybridized. That's because it's a triple bond. I really should put quotes around sp there too, but that's kind of the idea. So you can see there's the bond angles, there's the bond orders and the hybridizations. But the last part, does CO have a stronger bond than the other 2? And I would argue that it definitely does. Higher bond order means stronger bonds. Highest bond order definitely comes from CO. CO would have the highest, strongest bond order, bond energy, all right? CO2 would be next with a bond order of 2, and carbonate with a 4/3 bond order would be the weakest of all of those. Okay, so that's it for the video for problem set number 5 of Chemistry 221. If you have additional questions on the material or you need some more practice, make sure you check out the study guides, the concept guides, which are both in the companion and online. You can also look at the chapter guides, which are online only for additional material, how to get you started, how to get you situated up with this new material. All right, thank you for spending your time with me. I do appreciate it, and I hope this has been helpful. I hope you have a wonderful day. Thanks for being here.